Hi, in this video, I'll be solving questions from A-level Equilibria. For this particular video, I'll be solving questions from February-March 2019, paper 4-2. Question 1. C. At room temperature, N2O3 dissociates. N2O3 gas dissociates to give you NO gas plus NO2 gas. Write the expression for Kp for this equilibrium. Include the units in your answer. And so it means that the Kp is equal to the partial pressure of NO times the partial pressure of NO2 divided by the partial pressure of N2O3. And so for the units, you know that pressure is measured in pascals or atm or Newton per meter squared, but I'm going to use pascals for this. And so for this, Pascal times Pascal divided by Pascal. And so the Pascal here cancels 1 on top, and so we are left with Pascal. A 1.00 decimeter cube flask at 25 degrees Celsius is filled with pure N2O3 gas at initial pressure of 0.60 atm. At equilibrium, the partial pressure of NO2 gas is 0.48 atm. Calculate the partial pressures of NO gas and N2O3 gas at equilibrium. Hence, calculate the value of Kp at 25 degrees Celsius. So, for the initial partial pressure of N2O3, it has been given as 0.60. But at the start of the reaction, the initial pressure of NO and NO2 is 0.0. But the equilibrium partial pressure of NO2 has been given as 0.48. So it means for this, that will be 0.48. How do we get 0.48? The initial plus the change over here sum up to give you the equilibrium. So it means that if the initial is 0, then it means the change over here should be 0.48. Okay. Now, the mole ratio between the NO and the NO2 is 1:1. So it means the change over here should also be 0.48. Okay. But for the reactants, we have to subtract this change from this initial partial pressure. So it means for this one, it will be 0 minus 0.48, whilst these ones are plus 0.48. And again, you said the initial plus the change must give you the equilibrium partial pressure. So it means this one will also be 0.48. And so this will be 0.12. So it means the partial pressure of NO is 0.48 atm. And that of N2O3 is 0.12 atm. And for the Kp, again, it is equal to the partial pressure of NO times the partial pressure of NO2 divided by the partial pressure of N2O3. And so that is equal to 0.48 times 0.48 divided by 0.12. And so that should give you 1.92 atm. Question 2. The following table lists the solubilities of the hydroxides and carbonates of some of the group 2 elements M at 25 degrees Celsius. BI calculates the value of the solubility products KSP of magnesium hydroxide at 25 degrees Celsius. So when you have a question like this, the first thing to do is to write the dissociation equation for the magnesium hydroxide. Okay, and so that should give you Mg2 plus aqueous plus 2OH minus aqueous, while this is a solid. Now the solubility of the magnesium hydroxide has been given as 2.0 times 10 power minus 4. And so, since it is a source, when a source dissociates, okay, the concentration or the solubility, same as the concentration, will be the same as that of the ions. And so, since the mole ratio between the Mg2 plus ion and the magnesium hydroxide is 1:1, it means for the magnesium ion, that will be 2.0 times 10 power minus 4. However, for this one, is 1:2, so this will be 2 times 2.0 times 10 power minus 4. The KSV expression is giving us the products of the ions of the salts, concentration of the ions of the salts raised to the stoichiometric amounts. So this will be exponent 2. And so when you take the concentration of Mg2 plus is 2.0 times 10 power minus 4 times the concentration of OH minus, which is 4.0 times 10 power minus 4 exponent 2. This will give you 3.2 times 10 power minus 11. And I suppose the units will be mole cube decimeter minus 9. So you can try this. The unit for this is mole. For the magnesium ion is mole decimeter minus 3. And times the unit for the hydroxide, concentration of hydroxide ion is mole decimeter minus 3 exponent 2. And so I believe if you do that, you should get mole exponent 3 decimeter minus 9. II. State what will be observed if a few drops of a saturated solution of barium hydroxide are added to a saturated solution of barium carbonate. Explain your answer. So what will be the observation and what will be the explanation? Now, we are adding a saturated solution of barium hydroxide to a saturated solution of barium carbonate. If you dissociate barium hydroxide, you realize that you have barium ion, so Ba2+. And you also have the same ion in the barium carbonate, that's the Ba2+. So it means that as you are adding the barium hydroxide, you are adding more barium 2+ ion to the already existing barium 2+ ion in the barium carbonates. And so due to common ion effects, as you are adding more barium 2+ ions to the product side of the barium carbonate, the equilibrium is going to shift to the left side of the barium carbonate. So which means that you are going to form a white precipitate of the barium carbonate. So you are going to see a white precipitate, okay, precipitate. So when you are writing full, precipitates, okay, will be formed for barium carbonate due to common ion effect, okay, common ion effect. Question 3. A. Use mathematical expressions to define the following terms. So for this one, pH is equal to negative log concentration of H plus or negative log H plus ion concentration. And for Ka of a weak acid Ha, so for the Ha, when you dissociate Ha, you realize that you get H plus aqueous plus A minus aqueous. And so the Ka for this is going to be concentration of H plus times the A minus divided by concentration of the acid, which is Ha. II. Write equations to show how a buffer solution consisting of a mixture of Ha aqueous and NaA aqueous controls pH when an acid or an alkali is added. Remember, a buffer is a solution that resists changes in pH when a small amount of an acid or a base is added to it. And a buffer is made up of an acid and its conjugate base, or an acid and the salt. So in this case, NaA. Now, we can get the conjugate base from the salt. So this conjugate base over here, we can get it from the salt NaA. You know, a salt will always dissociate in solution to give you the ions in it. So plus A minus. Now, for this combination to act as a buffer, it means that first, when we add the base, a small amount of a base, so OH minus, is going to react with the acid, which is Ha. Okay, and you know what acids do? They donate a proton, and so this acid is going to donate a proton to the base, and so that is going to give you A minus, then plus H2O. Okay, all of them aqueous. The conjugate base, okay, from the acid, which is A minus, is also going to react when you add a small amount of an acid, okay, to this buffer solution. So H plus, I'm using H plus to represent any acid. So when you do this, you're also going to get HA. Okay, so this is how this buffering system, okay, acts as a buffer. These are the two equations. You write with a base, you write with an acid. B. When chlorine dissolves in water, the following reaction occurs. Cl2 gas plus H2O liquid giving you perchloric acid plus H plus aqueous plus Cl minus aqueous. When solutions of chlorine are used for water purification, the pH of the solution of chlorine is kept near to pH 7 by the addition of a base. Chlorine is dissolved in water to produce 1000 centimeter cube, which is the same as 1 decimeter cube of a solution containing 0.170 mole of HClO and 0.170 mole of ACl. A buffer solution is then prepared by adding 0.200 mole of sodium hydroxide to this solution. The sodium hydroxide reacts initially with the ACl. Calculate the pH of the buffer solution. And the Ka for the AClO has been given as 2.9 times 10 power minus 8 mole per decimeter cube. So we saw that in this question, when they first added the sodium hydroxide, they said it first reacted with ACl. So it means we first of all have to write an equation between ACl and sodium hydroxide. Okay, and that will give you sodium chloride plus water. Okay, the amount of the sodium hydroxide added in this case is 0.2 mole, and that of the ACl is 0.170. So I'm going to write that 0.17, okay, 0. Now, it means initially this will be 0, 0, but after the reaction, we can see that this is the ACl is the limiting amount. So all of the ACl will be consumed, okay. However, some of the sodium hydroxide will be left, which will later go and react with the AClO. So if we subtract 0.17 from 0.2, so we are getting 0.03, okay, 0.03. So this will be left of sodium hydroxide after this reaction. Now, to form the buffer, the amount of sodium hydroxide that was left after first reacting with the ACl is now reacting with the AClO. Remember, the buffer is actually formed between AClO and NaOH. So this is the amount of sodium hydroxide left after the reaction with ACl, and the amount of AClO is 0.17 as well, mole as well. But for a buffer, we need the concentration of the salt. How do we do that? Is by using the amount of the limiting reactants, okay, in this case, the sodium hydroxide, okay, use the mole and mole ratio to find the amount of the salt, okay. So initially this will be 0, 0, but at equilibrium, the sodium hydroxide will of course be consumed and some of the ACLO will be left. So to note that, you have to subtract the 0.03 from 0.17, and it means that at equilibrium it will leave with 0.14 mole of ACLO, but this was the limiting. Sodium hydroxide is the limiting. So if you use mole ratio between sodium hydroxide and the product, it means that the mole of this will also be 0.03 at equilibrium because it was consumed, okay, to form the products. And so this will also be 0.03. And since the mole ratio is 1:1, okay. So now that we know the equilibrium amount of the acid as well as the salts, we can find the concentration of the acid and the salt at equilibrium. And remember, concentration is equal to amount over volume. The amount of the acid at equilibrium is 0.14 mole, and the total volume of solution was 1000 centimeter cube, which is same as 1 decimeter cube, and so concentration is 0.14 mole per decimeter cube. For the salt, the equilibrium amount is 0.03 mole divided by the 1 decimeter cube, which will also give us 0.3 mole per decimeter cube. Now we know that pH is equal to pKa plus log concentration of the salts over concentration of the acid. And so you also know that pKa is equal to negative log of Ka. And so since you know we have the Ka, means our pKa will just be equal to negative log of the 2.9 times 10 power minus 8, and that should give us 7.54. And so it means that if we put that in this pH calculation, so we have 7.54 plus log, we know concentration of the salt is 0.03 divided by 0.14, and so the pH should be 6.87. 6.87. Thank you guys for watching. See you in the next tutorial. Do well to subscribe and leave a comment if you like this video. Thank you.